Welcome students to the course on Advanced Computational Techniques. Myself, Dr. C. SIVA from the Department of Physics and Nanotechnology, SRM Institute of Science and Technology, Chennai. In this, we will discuss much more deeper on the carbon nanoelectronics, how carbon nanoelectronics are actually being identified as a viable material for the futuristic electronics, which can replace or which can actually adjacently work with like silicon materials. In the last class, we had discussed about very clearly on the uh, troubles which we are actually facing at the nanoscale of the silicon. Carbon nanotube electronics. Carbon nanotubes or carbon CNTs, which are actually quasi one-dimensional materials with very unique electronic properties. Because electrons can travel through them with very little scattering. They are excellent candidates for high performance electronic devices. Recent progress shows that CNT transistors can be made without doping by controlling the contact between the metal and the nanotube. This actually allows CNT FETs to keep their perfect atomic lattice and potentially outperform modern silicon devices. Both N-type and P-type CNT FETs can be actually developed, and CMOS style circuits as well as fast transistors logic have been explored. Here you can actually see this is the graphene sheet which is being rolled up, will be called as carbon nanotube. In general, this carbon nanotube will get a cap here, and another one half of the fullerene will be actually acting as a one side cap, and another half will be actually acting as another cap. Okay, and by making a breaking or a cleavage over the surface, okay, we can actually introduce the uh, doping, okay, which will actually act as a semiconducting material. Okay, so till this it is actually a conducting material, and here semiconducting material. We can actually induce the band gap values by means of opening the surface of the carbon nanotube like this way. This is what we have actually explained in the previous. Both N-type and P-type CNT FETs. Okay, sorry here. Both N-type and P-type CNT FETs near the ballistic transport performance limits have been actually been fabricated. So ballistic transformance the performance, which means a negligible quantity of resistance kind. Okay. So symmetric CMOS devices have been actually demonstrated, and pass transistor logic are actually being developed, and they are actually efficiently working. Why CNTs are actually promising? The main reason CNTs are attractive is their extremely high mobility due to their sp2 carbon bonding. CNTs can also use wrap around gate structures, giving excellent electrostatic control. While other high mobility materials like indium gallium arsenide have shown potential, but they face integration challenges, especially for CMOS logic on silicon substrates. Silicon demonstrated because CMOS offered high noise immunity and low static power. But CNT CMOS could provide further gains by reducing switching energy and heat generation. See, one another about CNT here. Okay, we'll see here. CNT development timeline and motivation. CNTs have long been known to have the right electrical, thermal, light, thermal, electrical, mechanical, and chemical properties to be an ideal electronic material for next generation electronic devices. It took nearly 15 years, okay, from the first CNT FET, which is actually identified in 1998. Okay, 1998. Okay, to the appearance in the first CNT computer. The motivation comes from the fact that silicon CMOS was predicted to reach its physical scaling limits uh, around 2020 itself. Beyond that point, further improvements in speeding and energy efficiency require new channel materials such as CNTs. Why CNTs are actually promising? Again, been given here. See, the CNTs are actually attractive again due to the sp2 carbon bonding. Sorry, CNTs can also use wrap around gate structures, giving excellent electrostatic control. Again, while the other high mobility materials like indium gallium arsenide have shown potential, but they face integration challenges while they are actually making in terms of CMOS logic on silicon substrate. They find several issues. Main issues is actually again integration challenges. Silicon dominated because CMOS offered high noise immunity and low static work. But CNT CMOS could provide further gains by reducing switching energy and heat generation. CNT versus other emerging technologies. Studies from IBM and Stanford compared CNT MOSFET technology to the silicon nanowires and tunnel FETs. You can see here uh, in this, okay, where CNT MOSFET technology to silicon nanowires and tunnel FETs, because it is worthy to compare the silicon of wire shape and carbon nanotube, since they both are actually geometrically same. Because at nanoscale, geometry is actually very important one. Okay. CNTs showed a clear improvement when scaling to 8 nanometer to 5 nanometer. Okay. CNTs had actually shown clear improvements when scaling from 8 nanometer to 5 nanometer. Okay. Here you can see. It has been stopped in terms of silicon, we can say. But in terms of carbon nanotube, we can actually see improvements. Okay. It's been possible. Okay. Heavily been improved. Equivalent. Equivalent. Okay, they are. CNT CMOS FETs are predicted to outperform silicon by multiple technology generations and fabrication methods using aligned CNT arrays on silica or quartz enable high performance devices without chemical purification. CNT thin films and graphene limitations. CNT thin film electronics mix metallic and semiconducting nanotubes, requiring purification or breakdown to remove metallic parts. These can be useful for flexible or stretchable electronics, radios, and mixers, but electrical performance is compromised in these devices. Graphene, although it has very high mobility, it does not have any natural band gap so it cannot act as a digital switch. Cutting graphene into narrow ribbons introduce scattering, making it inferior to CNTs for logic devices. Let's see the fundamentals of FET. Integrated electronics has advanced mainly by scaling the FETs, mainly by scaling the field effect transistor. Yeah, FET has source, drain, and gate. You can see here it has a source, it has a gate, it has a drain. A channel and a gate dielectric. There is a channel. Okay, here it is actually acting as a channel. Channel length is actually mentioned here, and there is going to be a oxide layer which acts as a dielectric layer. That is called a gate dielectric. The gate voltage controls current through the channel. The gate voltage controls the current through the channel. Two key parameters define switching. Two key parameters define switching. Transconductance make transconductance which measures amplification strength and subthreshold swing, which measures how quickly the device switches from off to on state. Again, I'm mentioning transconductance, which measures the amplification strength. Then subthreshold swing, which measures how quickly the device switches from off to on. Off to on is actually known to be SS, subthreshold swing. Swing from the state. Okay, you can remember like that way. Then another is called transconductance. Okay, amplification strength. Ideal SS at room temperature is 60 millivolt per decade. Okay, subthreshold swing and CNT advantages. In a long channel silicon FETs, SS typically lies between 60 and 80 millivolt per decade. Okay, 60 millivolt and 80 millivolt per decade. You can actually see here 80 millivolt per decade. But when gate length is actually going to reduce to below 20 nanometer, silicon loses tight control of channel current. CNT FETs with gate length around 9 to 15 nanometer. Okay, gate length even 9 to 50 nanometer. Okay, so in that SS values as low as 74 millivolts per decade due to their unique band structure and ultra thin body. So here you can actually see. So these values are actually lying lesser than 80 millivolt per decade. So this is very good value when compared to the silicon values. Okay. This makes CNT CMOS most promising candidate for scaling down to 5 nanometer nodes. History of CNT FETs and Schottky barrier devices. The first CNT FETs were made using backgate structures. The first CNT FETs were made with backgate structures. Unlike silicon, CNTs are naturally intrinsic and cannot be reliably doped. Any reliable doping methodology is not actually viable for CNT. Doping would disrupt sp2 lattice, reducing the mobility. As a result, early CNT FETs were Schottky barrier devices where the polarity was determined by the metal CNT interface rather than dopant atoms. This limited performance and slowed the CMOS development. It has been explained in this slides. You can actually go through by keeping the pause button. Yes, in this slide, there are a basic history and the CNT effects are being given. which is a Schottky barrier device. You can see here. The first CNT FETs were first CNT FETs were actually obtained by means of backgate structures. Okay. There is a limited performance and a slowed CMOS development. The next is called perfect ohmic contact CNT FETs. Later research showed that perfect ohmic contacts can be made to CNTs. Palladium contacts the palladium contact the valence band giving p-type behavior, while the scandium contacts the conduction band giving n-type behavior. P-type behavior from the palladium contact and the n-type behavior from the scandium contact due to the charge carriers available in those materials. These devices operate close to the ballistic limit. The scandium contacted device shows high on current linear conduction even at 4.3 Kelvin, confirming the barrier free junction, which is being explained in this graph. You can see here and also this one. Okay, both are actually scandium contacted backgate. Okay, so which is the first one is actually the transfer characteristics and the second one is actually the output characteristics. Self-aligned CNT FETs. Like silicon integrated circuits, CNT technology adopted self-aligned gate fabrication. Self-aligned gate fabrication to minimize alignment errors. Self-aligned gate fabrication to minimize the alignment errors. Self-alignment structures ensure precise positioning of gate, source, and drain, which enable short channeling length. Without overlap, advanced designs now include gate-around geometry, giving even better electrostatic control, which is essential for CMOS logic at nanoscale dimensions. Let's compare silicon FETs to the CNT FETs in terms of performance metrics. CNT FETs can be benchmarked using intrinsic gate delay and energy delay product. Intrinsic delay depends on CV by I, where C is gate capacitance, V is the supply voltage, and I is the on current. A CNT FET with a 120 nanometer channel shows an intrinsic delay of 0.86 picoseconds, fast enough, which is fast enough for terahertz range operations. Its energy delay product is far lower than the silicon devices of the same length. Again, I'm repeating, a CNT FET with 120 nanometer channel length shows a intrinsic delay of 0.86 picoseconds, which is much faster enough for terahertz range applications. Its energy delay product is far lower than the silicon devices of the same length. We'll see the the earlier discussed things are actually being given here. In this, we'll actually see about the scaling benefits. When CNT FETs of different lengths are compared to silicon MOSFETs, CNT devices show much better scaling trends. A 120 nanometer CNT FET is actually 5 times faster than a silicon MOSFET of the same length and consumes about 1/100th of the energy. This is due to the quasi-ballistic electron transport and a high Fermi velocity in CNTs. Again, I'm repeating here, While carbon nanotube field effect transistors of different lengths, okay, of different lengths, which are compared to the silicon MOSFETs. CNT devices shows much better scaling terms. 120 nanometer CNT FETer is 5 times faster than the silicon MOSFET of the same length and consumes only about 1/100th of the energy. This is due to the ballistic electron transport nature and high Fermi velocity available in the carbon nanotubes. Okay, you can actually go through the graphs and the corresponding explanations so that you can actually understand much more details in a better way. So with this, I feel like you can actually go through the thing and we'll actually discuss the next module from the next lecture videos. Thank you, students.